So it's a great pleasure to be here with all of you, even virtually. So many thanks to the organizers and MITP for making this possible. So I'm going to talk about the so-called chiral anomaly. This is non-conservation of chiral charge that we know happens in field theory with real electric and magnetic gauge fields, but can also happen with synthetic gauge fields induced, for example, by deformations of the crystal if we have chiral quasi-particles in the crystal. And I will focus on discussing this phenomena using usual notions of semi-classical picture, where particles move along trajectories in phase space, and we incorporate chiral anomaly semi-classically in this description. So this is the work done by my students and myself. Lan Gao is an exchange graduate student who spent a year with us at Stony Brook from Fudan University. So she arrived just before the lockdown, visited Stony Brook once, and then spent the rest of her visit sitting in her apartment and already went back. Sahal Kaushik is my student who will graduate in the summer and become a fellow at Norditer. And Ivan Philippe graduated recently and became a postdoc in quantum computing group at Brookhaven. Okay, so this is a cross-disciplinary workshop. So I would like to start by explaining the concept of chiral anomaly using an example from condensed matter physics. So suppose I have some material with a band, parabolic band of this shape. And suppose that Fermi energy is somewhere here around 0. So then if I focus on the energies which are close to Fermi energy, then I see that I have approximately linear right-handed particles which move to the right, and approximately linear band for left-handed particles which move to the left. And using external electric and magnetic fields, I can organize a flow of particles along this band. So I can create, let's say, right-handed particles, and I can make left-handed holes. And so far, there is no anomaly here. So the notion of anomaly emerges when I decide that I want to limit myself only to this effective theory of low energy particles. And I regularize the system by introducing an ultraviolet cutoff, let's say somewhere here near the bottom of the band. And in quantum field theory, I have to do it to regularize my quantum field theory. So then what happens is now you see that if I have a flow along this band, then in my effective low energy theory, this flow would lead to disappearance of left-handed particles and emergence of right-handed particles out of from this ultraviolet cutoff. So I will have a non-conservation of chiral charge. It is associated with the presence of ultraviolet cutoff, but nevertheless, it looks intuitively plausible that I can still apply some semi-classical description of this left and right moving quasi-particles, and that this chiral anomaly therefore can have macroscopic effects. And it appears, and of course, this is quite well known, that this by now that these effects can be captured by using semi-classical kinetic theory description with essential modifications that I'm going to discuss here. So of course there is a lot of literature written on this topic. And there are many statements in the literature that somewhat that contradict each other sometimes. So, for example, you can find a statement that once you induce quantum effects through Berry curvature, then the phase space element is no longer conserved. So you don't have a Hamiltonian flow in phase space. There is a statement that chiral anomaly is not at all related to Berry curvature. So I would like to start with reviewing the existing approaches, just presenting my viewpoint on them. And then towards the end, we'll come to an original part of this presentation, which we found with my students, where it appears that there is a particularly convenient way to formulate chiral anomaly and kinetic theory by introducing so-called what we call monopole charge function, describing a singularity in phase space. Okay, so let me just start by presenting a brief summary, pictorial summary of this talk. It basically says most of what I'm going to tell in more detail. So this picture presents the case of a spatially homogeneous systems where the only source of anomaly is electric and magnetic fields. And what happens in this case is I have two copies of left and right-handed phase space for left-handed particles and phase space for right-handed particles. And it appears that the anomaly, in fact, does not violate the preservation of phase space elements itself. However, anomaly introduces a source and a sink in the left and right-handed phase spaces. So the origin of this anomaly is this Berry monopole in P space. And then you have this kind of wormhole which connects the space of left-handed, phase space of left-handed particles and phase space of right-handed particles. But other than the presence of this source or sink, the flow in phase space is Hamiltonian. And then if we deal with spatially inhomogeneous and time-dependent systems, for example, if I have a crystal which I subject to torsion and time-dependent compression, then the picture gets modified in this way, where again, everything is just like on the previous slide. But the monopoles that emerge are monopoles in phase space, and they can be characterized by these monopole charge functions, which have some interesting symmetry properties. And once the symmetry properties are used, then one can formulate in a very simple form an effective kinetic theory. Okay, so just to remind you what Liouville theorem is, of course, all of you know what it is from classical mechanics. So if you have a classical system characterized by some phase space density, then its convective derivative is equal to 0. So distribution function is constant along any trajectory in phase space described by Hamilton equations. And you have this conserved current. Okay, so another way to think about this is that the flow of phase space is incompressible. So you have this Hamiltonian incompressible flow. And this can also be characterized using Poisson brackets, using Hamilton's equation. This formula here can be recast in this simple form, which involves the Poisson bracket of the phase space density and the Hamiltonian. So the meaning of this, again, is the phase space measure is invariant under Hamiltonian flow in classical mechanics. So then, of course, when we learn all of it in our classical mechanics 101, we are probably taught that phase space, an example of a symplectic geometry, and what we deal with, the element of phase space, is a symplectic form element. And of course, this is nice and beautiful and formal, but usually we don't really use it in any computation we do in classical mechanics. But we will see that in our particular problem, this is really a crucially important fact about Hamiltonian flow. So in this case, the Liouville theorem is formulated in the following form, that the Lie derivative of the volume form is 0 along the flow generated by the Hamiltonian. Okay, so now what happens when we start to talk about quantum mechanics? Then in quantum mechanics, we replace the Poisson bracket by the commutator. We talk about evolution of some mixed state. And so the question is what happens to conservation of phase space? So this was addressed, of course, in classic papers by Weil, Wigner, and Moyal. And we know that in quantum mechanics, the fluid, phase space fluid is no longer incompressible. There are indeed quantum corrections to this equation. So one can define so-called Moyal bracket. And so one possibility that comes to mind is that maybe the chiral anomaly, which is a quantum effect, enters through this quantum corrections to Liouville equation. However, the answer to this question is negative. And to understand what happens, we have to consider the notion of Berry connection. So suppose we have a classical particle with quantum mechanical particle with some momentum p. We bring it along some smooth contour. So this is a slow adiabatic motion. And as a result of the motion, the wave function of the particle picks up a phase. There is a corresponding Berry connection, which is analog of gauge field. And one can define the corresponding Berry curvature, which looks like a corresponding effective magnetic field. Okay, so now if you take the classical action for this system, Then the classical action for a system in the presence of Berry curvature contains this extra term, which couples Berry connection to time derivative of momentum. And the physical quantity is the curl of this connection, the curvature. And if you consider this curvature for a massless Weyl fermion, then you end up with this singularity at zero momentum, which is a consequence of the band degeneracy for massless fermions. So the point is that even if you try to be very careful and move the particle very slowly, even very slow motion for this intersecting bands can cause a transition between the bands. And this is why we get this singularity at so-called diabolical point. Okay, so then once we have identified the presence of this singularity, we can define we can evaluate the equations of motion. So this is how they look like. And we find that the motion of our otherwise classical particle now is affected by the presence of the Berry curvature if we have external electromagnetic fields. So note that if no electromagnetic fields are present, then Berry curvature does not have any effect on the motion of the particle. But if electric and magnetic fields are present, then you see that there are terms describing anomalous Hall effect induced by Berry curvature and the chiral magnetic effect induced by the asymmetry between left and right-handed fermions. Okay, so now what happens to the Liouville theorem? So if you just use this formulation in background Berry curvature and supplement the equations on the previous slide by Maxwell equations, you can easily find that the phase space element in this case is no longer conserved. So instead of 0 on the right-hand side, you get E dot B, which is the source of chiral anomaly, multiplied by delta function at P equals to 0, which of course is the consequence of singularity of the Berry curvature. So now, again, the question is, we see that phase space flow is not incompressible, it is compressible. And so the question is, does it stem from non-Hamiltonian flow of phase space itself? And the answer to this is no. The flow of phase space elements is perfectly Hamiltonian, but you actually just have an extra source in this equation. And there is a way to see it because in the presence of magnetic field and Berry curvature, the variables x and p are no longer conjugate variables in phase space. We have to really invoke this general theory of symplectic space and define properly the Poisson brackets and the corresponding symplectic form and the matrix inverse of this form. And once you do this properly, you realize that the phase space elements have to be modified. And once you redefine the phase space element, then without the anomaly, the flow in this phase space is perfectly Hamiltonian, and only the singularity of Berry curvature is the source of anomaly. So here is this picture. I have a Hamiltonian flow, and you can just think of some source and sinks for this phase space fluid, which otherwise flow according to Hamiltonian dynamics. Okay, so now let me come to the main subject of the talk after this extended introduction. Suppose I want to describe anomaly in spatially inhomogeneous and time-dependent systems. So as a particular example, you can think of a wire semi-metal, a material which supports left and right-handed chiral quasi-particles. And let me assume, and it is very often the case, that the effective Hamiltonian describing these quasi-particles has this form, where generalized momentum P can be a function of momentum, coordinate, and time. So this encodes external electric and magnetic fields and elastic deformation of the crystal. And this phi here is kind of a potential, which in a crystal can also carries information about, for example, a tilt of the Weyl cone induced by deformation. So then I write again the classical semi-classical action for these particles. I can define now the Berry curvature, the Berry connection and Berry curvature, but this time because I have the system where deformation affects simultaneously both momentum and coordinate space, I can define an object which is a Berry connection in phase space. So in x in coordinate and momentum space. So index alpha here can be coordinate, momentum, or time. And so this is how it is defined in terms of the usual Berry connection. And here is the corresponding Berry curvature. So now we have found that for our type of Weyl Hamiltonian, this Berry curvatures satisfy this very important equality. So they have this interesting symmetry property, which can be proven for any type of the Weyl Hamiltonian that I showed you before. And once we use this equality, then we find that the Liouville equation can be written down in this form, where theta is an exterior derivative of the Berry curvature in phase space. And because it really plays a very important role both in Liouville's theorem and in kinetic formulation, we introduced a special name for it. We call it the monopole charge function. So this is how it's defined. Once you evaluate Berry curvature in phase space, then this monopole charge function is an exterior derivative of this Berry curvature. So now again, we see that without this monopole charge function, we have a perfectly Liouville Hamiltonian flow, but this monopole charge function sources the non-conservation of phase space for left-handed and right-handed particles. So again, you have this source and sink for left and right-handed distributions. So now, again, using this simple properties, symmetry properties of monopole charge functions, we can write down the kinetic equations. And this is how they look like in terms of Berry curvature in phase space. So we can do a quick consistency check. So for example, suppose I have no deformations in the crystal. So then my momentum is simply k minus a using Poirot's substitution. Then I take my monopole charge function, where alpha, beta, and gamma, for example, if you pick alpha as momentum, beta as coordinate, and gamma as time, then derivative of this generalized momentum with respect to time gives you electric field in Coulomb gauge, and derivatives with respect to coordinates give you magnetic field. So you end up with E dot B times the singularity at P equals to 0. And if you look at other components, then you find this identity. So for the case of pure electromagnetic background with no deformation, you recover the previous Liouville anomaly and the usual kinetic equations. However, the situation becomes more interesting if we now consider the case of a crystal which is being deformed. So a particular interesting case is the case when the crystal is subjected to simultaneous torsion and time-dependent compression. And this is something that we looked at before with Alberto, Carol, and Maria. And there was also a work by Marcel Franz and Dima Pikulin. And there are other papers on this subject as well. So the reason why this particular case is so interesting is because torsion induces for you a synthetic magnetic field, as you can explicitly check using the formulas that I showed before. And compression induces a synthetic electric field. So you can call it, gravimagnetic and gravi-electric fields because they result from deformation of the metric. And if you look at the anomaly equation in the presence of this torsion and time-dependent compression, then you find that for an isolated cone of a particular chirality, this synthetic magnetic and electric fields actually act exactly in the same way as the usual electric and magnetic fields act. They lead to non-conservation of chiral current. So we, in fact, looked at a particular tight binding Hamiltonian, which for the benefit of time, I'm not going to write now. And we observed that in this tight binding Hamiltonian, and we suspect that this is actually a general case, what happens after you look at this combined effect of synthetic electric and synthetic magnetic fields is that the total chiral charge that you generate after summing of the overall left and right-handed wire count is actually equal to 0. So this is kind of generalized Nielsen-Ninomiya theorem for this space-time dependent backgrounds. However, because the chiral magnetic effect is driven not by the chiral charge itself, but by the chiral chemical potential, what happens is that in general, the deformation induces asymmetries between positions of left and right cones. And as a result, you no longer have a cancellation in the chiral magnetic current. So in other words, the sum over chiral chemical potentials over different wire cones does not vanish. And so for some case where this is due to some non-equilibrium phenomena, this is something that we looked at with Yuta Kikuchi and René Meyer. So again, in these papers that I already mentioned, this was induced by strain. And so here we explicitly, in this paper, we explicitly evaluated this for a particular tight binding Hamiltonian. And we found that even though the total chiral charge vanishes, the sum over chiral chemical potentials does not vanish. And so what it means is that I cannot drive a chiral magnetic current by synthetic electric and magnetic fields alone. What I can do is I can put my crystal in an external electromagnetic magnetic field, then subject it to torsion and compression, some combination that gives me synthetic E dot B. And in this case, I will indeed induce a chiral magnetic current of the type that we considered with Alberto, Carol, and Maria. So this is how the corresponding experiment would look like. You take a wire crystal, you subject it to torsion or time and time-dependent compression. You can also consider a crystal which has some static torsion built into it. And then in response to time-dependent compression in a magnetic field, the crystal would generate an electric current, a chiral magnetic current in it. So now the numerical estimates, unfortunately, depend a lot on the particular parameters. Well, maybe it's actually fortunate because you can tune the parameters of your material to make this current quite large. So without a particular attempt to tune the magnitude of this current, we estimated for a particular tight binding model that we used, that if you have a millimeter by millimeter crystal, put it in a magnetic field of about 10 Tesla, subjected to this twist and compression, you find the current on the order of nanoampere. And this is actually quite comparable to what people observe in transport in these materials. Okay, so my time is almost up, and I would like to leave a few minutes for discussion. So instead of a summary, let me just show you this image again, which illustrates what happens to chiral systems with wild fermions in the case of spatially inhomogeneous and time-dependent deformation. You get a Hamiltonian flow of left and right wild particles, but there is a source and a sink caused by the anomaly, and this source and sink induce very interesting transport phenomena that can be observed with this synthetic gauge films. So thank you very much for your attention, and I look forward to your questions.
Thank you very much for a very interesting talk. We have time for questions. Yes, please unmute yourself and ask.
Hi, thanks for the talk. I just had a question. Often in the language of anomalies, and most precisely in the case of synthetic E and B fields, we talk about covariant anomalies versus consistent anomalies. How does your computation of the Liouville anomaly takes care of these two kinds of anomalies?
Okay, so in my mind, the main advantage of formulating things in the language of Liouville anomaly is that you do not have to think about the distinction between covariant and consistent forms of the anomaly. So you just have, physical equation of motion for, in your kinetic theory. You immediately obtain physical results for the current. And so this issue, which, indeed is very important, as you clearly know, this subtlety, I think, does not really emerge in these equations.
We have another question by Jacopo, please. Jacopo,
I think you are muted.
Can you hear me now?
Yes.
So thanks a lot for the very inspiring talk. I have a curiosity about the possibility of investigating your proposal using not electronic systems, but photonic Weyl systems, like the ones that have been done using photonic crystals or using, say, lattices of electric circuits.
Yeah, this is a very interesting question indeed. I think if you find a way to realize anomaly in a photonic crystal, then, and I know that people discuss this, I think this phenomena should be present there as well, and it would be really a great way to simulate these anomalies using some photonic crystals or cold atoms or other systems. This would be extremely interesting. So do you have some particular realization in mind?
Yes, I would have, naturally, I would move towards one of those photonic crystals or topoelectric circuits where you can inject particles very selectively in both position and momentum. And then you can follow in time the evolution according to, say, the equation of anomalous Hall transport and all that.
I
So
see.
for that, the only doubt I have is whether a while system is enough for what you're proposing, or you have something more subtle in mind.
Well, for example, normally to have anomaly, chiral anomaly with while fermions in usual electric and magnetic fields, you must have these fermions interacting with electric and magnetic fields, right? So you need charged while fermions.
Okay, but you can have synthetic charge and
Yeah,
synthetic
exactly.
magnetism.
That's exactly what I was going to say. But here, the advantage of this synthetic fields is that the while fermions do not even have to possess, real interaction, do not have to possess electric charge to observe this anomaly. So the Liouville anomaly in kinetic description, or the chiral anomaly in field theoretic description, still appears there. So and you can model it using, for example, photonic crystals. So the only thing that we found is that you cannot drive chiral magnetic current using synthetic fields alone. But you definitely can create chiral charge density using only synthetic field.
Okay.
So you would not be able, if you don't have charged while fermions, you would not be able to simulate chiral magnetic current, but you would be able to simulate non-conservation of chiral charge.
Mm-hmm. Good, thanks. Looks exciting.
Thank you.
Yeah, I think next question is by Johanna.
Yes.
Hello,
Hi, Dima. Hi, nice to see you.
Okay.
Hello. Well, I was going to ask a question about torsion, but since the discussion went to topologic circuits, I have a quick question there also. I mean, for me, a chiral anomaly is still a quantum effect. I mean, how would you, as I understand, topologic circuits are still something which is inherently classical. So how would you implement an anomaly there at all? Sort of, maybe you can clarify this. But my other question was about torsion. I mean, you mentioned these effective electric and magnetic fields which are generated by torsion, and I wonder if you could be a little more explicit why torsion has this particular effect on this, or why can you model torsion just for this particular magnetic field, and can you elaborate a little more?
Okay, so let me first try to answer your first question. So of course, chiral anomaly is a quantum effect, so we both agree on this. But the point that I tried to make is that this quantum effect appears as a source in otherwise Hamiltonian flow of phase space density. So if you think if you try to incorporate this quantum chiral anomaly in semi-classical description, then the picture that you have is really everything here flows like an incompressible fluid. But for this incompressible fluid, you have either a source or a sink, depending on the size of on the sign of E dot B. So this is the only meaning in which I talk of it as some kind of semi-classical phenomenon. Of course, the origin of this anomaly is purely quantum. So.
Okay, but sorry, can I just ask more? But then how would you realize this in these topologic circuits? I mean, can you make use of this phase space?
Yes, so now we come to, actually this is tightly linked to your second question, what is the origin of this synthetic E dot B, right? And so basically you can see what happens here is if you deform your crystal in such a way that generalized momentum now becomes also a function of coordinate. So for instance, you can think of this function here becoming a function of coordinate as a result of twist. Then you can easily see that the monopole charge function, defined like this, can give you E dot B from just the dependence of Berry curvature on coordinate. And for a particular twist deformation, the quantum numbers are such that you really get this E dot B. So you basically get the twist gives you a curl of a synthetic gauge field, and the time-dependent compression, once you differentiate this with respect to time, it gives you a synthetic electric field. So basically, to induce the synthetic anomaly, you always have to combine a torsion, which would give you some synthetic magnetic field with some time-dependent compression, which would give you a synthetic electric field. So, and if you have some classical circuit with chiral fermions, then and you are able to induce the synthetic E and dot B, then I think in principle it should be possible to emulate anomaly in this system, just similarly to what happens in a Weyl semi-metal.
Yeah. Okay. Thanks a lot. Yeah.
Mm-hmm.
Our next question is by Renee.
Yeah, hi, Dima. Thanks for the nice talk. Hi. I had a question. So, do you think one can incorporate discrete anomalies like the parity anomaly in 3 dimensions also in such an effective framework?
That's a very good question. So, for parity anomaly, of course, we would be talking about some 2-dimensional system, right? And then basically, I guess what one could think about is parity anomaly induces electric charge in the presence of magnetic flux, yeah. Right? So, so what the question that would be interesting to explore whether a deformation, whether you can have a particular deformation that induces synthetic magnetic flux, and whether this synthetic magnetic flux could generate a background electric charge. So basically, I would take some film, and then for a particular deformation, you know, I would generate some background electric field. It's a very good question. I haven't really thought about this, but it's I think it's a great question to think about.
Okay, okay, thanks. Yeah, maybe we can discuss a little more.
Yeah, absolutely.
Yeah.
Thank you. Our next question is by Maura. Oh, please, Maura.
Hey, thank you very much for the talk. Can you hear me?
Yes, yes, yes.
Excellent. So my first question is maybe rather naive, because I was not very familiar with these synthetic E and B fields. So the question is whether the fermionic charge, when coupled to these synthetic fields, is conserved or not. Is it observable rather than conserved?
First of all, of course, this synthetic electric and magnetic fields is by no means our invention. You know, people like Maria Vazmediana and her collaborators were talking about this for a very long time. So synthetic fields themselves, you know, have a very long history. So in terms of their coupling to electric and magnetic fields, so in order to generate asymmetry between left and right-handed charges, they do not have to couple to electric and magnetic fields. So you can generate asymmetry between the density of left and right-handed particles, even if they are not coupled to real electric and magnetic fields. However, if you want to utilize the asymmetry between chemical potentials of left and right-handed particles, so this is what this object here stands for. This mu A is really the difference between chemical potential for right-handed and left-handed chiral particles. So if you want to convert this asymmetry into electric current, then of course these chiral quasi-particles have to couple to electric charge in an external magnetic field. So the coupling to electromagnetic field is not necessary for anomaly itself, but it is necessary to generate the current, because then you invoke electromagnetic chiral anomaly.
Okay, so I'm not sure if I understand well, but I would have to read a little bit more. But maybe I can rephrase my question. As far as I understand, the issue with chiral anomaly is that we cannot make both chiral current and electric current to conserve quantum mechanically both at the same time.
Yes.
And we happen to choose to conserve the electric current because that's observed and not the chiral current. So I was wondering whether in this case we could choose freely among the two in case the electric charge, this electric charge were not observable.
Yes, so your notion of anomaly is completely correct. So as you can see here in this kind of naive picture for the wire semi-metal, so here when I have this spectral flow along the band, the number of right particles minus left particles is not conserved, because I create right-handed particles and annihilate left-handed particles. But because these are particles and these are holes, the electric charge is always conserved. So here, once I introduce ultraviolet cutoff, then the chiral charge is no longer conserved, because in my effective theory, left charges just disappear behind this cutoff, and right-handed particles just appear mysteriously from behind the cutoff. But the total electric charge is still conserved. So at least in this while semi-metal formulation, the choice is the same as in field theory. So axial current is not conserved, but electric current is conserved. So I don't know how to, of course, I agree with you that in principle, we could make a different choice, but in this particular system, I don't know how to make a different choice.
Okay, thank you very much.
Thank you.
I think we have another question by Baptiste. Please.
Yes, thanks. My other question is pretty related to a previous one. Can you, in principle, prove or find with your formalism the gravitational anomalies which are also present in the conservation of Gmu and Gmu5 in such materials?
That's a good question. I haven't really thought about this, so let me not say anything stupid. Let me just think about it. It's a good question. I don't know. I don't have an immediate answer for you. I would have to think about this.
We also have question. We have question from Adolfo. Please, Adolfo.
Hi. Very nice talk. Actually, a lot of ideas came to mind in your talk, so it was really, really nice. So there are these generalizations of vials with extra crossings. So is it correct to say that the difference there would be that your results would be, let's say, proportional to the monopole charge, or is there any other effect? I'm asking this because there's some possibilities in condensed matter that maybe in high energy are a bit less explored, like for example, 3-band crossings that would effectively realize a spin 1 type of fermionic excitation, which in high energy is a bit, it's impossible because of Fermi statistics. But
I think that this formulation in terms of this monopole charge functions, I think is sufficiently general, because the way they appear in Liouville anomaly and in kinetic equations suggest that this is a sufficiently general formulation. So what I would try to do is, let's say, if I have this 3-band crossing, I would try to evaluate the corresponding Berry curvatures and find the corresponding monopole charge functions, and then see what does it imply for Liouville anomaly and for kinetic theory. I think it's a very interesting problem.
Yeah, there might be a complication because there, sometimes multiple bands at the Fermi energy, and maybe that kind of allows a bit of more freedom and possibly non-abelian fields in your language.
Oh, yes. Okay, so yes. Well, yeah, so this can be generalized to non-abelian Berry curvature, I believe. So I think that there should be a possibility to incorporate terms in both Liouville anomaly and then kinetic theory, which would correspond to, let's say, E A B A. So sort of sum over non-abelian charges of synthetic electric and synthetic magnetic fields. I think it should be possible to include non-abelian synthetic fields. So we haven't done it, just to be clear, but it looks plausible to me.
And maybe a final question. So there's, I think, even a more exotic anomaly that now been discussed now. This a mixed axial gravitation anomaly. Is there a semi-classical? So this picture is very nice, and it would be nice to have a semi-classical picture of that anomaly as well.
Yeah, exactly. So this is somewhat related to an earlier question. So I agree this would be extremely interesting to explore. And I see that Carol has his up, so maybe he has something to say about this.
Can I ask?
Yes, sure, please.
Okay. Yeah, thanks, Dima. Was very beautiful.
Thank you, Dima.
Talk. Unfortunately, I have nothing to say about this particular question. But because my problems are more basic. Can you enlighten a little bit? I mean, Fujikawa made this criticism saying that actually the chiral anomaly has nothing to do with the Berry curvature. But then again, it seems in your formalism, the anomaly again just comes from the singularity in the Berry curvature, right? The monopole. Yes. So can you expand a little bit? What is the criticism of Fujikawa, and if it applies or not? Or?
Well, so Fujikawa makes the point that Berry curvature is not related to anomaly, because if you derive an effective action, then one of them contributes to the real part of this effective action, and another contributes to the imaginary part of this effective action. And I think there is nothing wrong about his formulation in terms of this effective action theory. So my point is that if you just want to operate semi-classically at the level of this Liouville flow and kinetic equations, then the Berry curvature does reproduce correct effects of anomaly in this semi-classical description. So now, once you go to more general formulation, let's say effective action description, then of course, Berry curvature fails to completely capture effect of the anomaly, because remember, the notion of Berry phase was introduced for really some adiabatic, loops and so on. And such things simply, do not make sense in general in QFT formulation. So this is just my own personal understanding of the problem. So I agree with Fujikawa that Berry curvature is not completely general representation of the anomaly, but I think that once you limit yourself to semi-classical kinetic Liouville description, then Berry curvature is a perfectly adequate object to capture the effect of the anomaly. That's just my personal view on this problem.
Okay, and I have one more question, another question. So in your setup, you always switched on like parallel electric and magnetic fields, like real electromagnetic fields, or parallel effective fields?
Yeah, so both. So of course, for electric and magnetic, it's kind of it just follows from this monopole charge functions if you don't have any deformations. But if you do not have electric and magnetic fields and you only have this deformations, then anomaly is sourced by the synthetic magnetic and electric.
But my question is, what happens when you apply a usual magnetic field, or say do a deformation like this, twist the crystal to get this effective B field, and then not apply an electric effective field, but a real electric field?
Yes. So these terms. Just a second. Let me. Yeah, we also have such terms. So we found that in this case, the total kind of electric current summed over all while cones still vanished. So that's why we considered, so to generate the current, that's why we considered the setup when we have this B effective dot E effective to generate a chiral charge. And then we used an electric external magnetic field. But there are indeed terms which are cross terms between synthetic and real electric and magnetic fields, but their contribution to the currents, at least in the model that we looked at, vanished. I don't know if this is a completely general statement or whether it's a property of a particular kind of tight binding models that we looked at, but this is what we found.
Okay, thank you.
Mm-hmm.
Maybe.
Yes, we have a question from Maxim.
Good morning, Dima. Nice talk. I just want to, in fact, my question was a little bit inspired by a question from Carl. I just want to ask you that, in fact, when we deform the crystal, we expect to get in particular the axial fields. which act differently on left-handed and right-handed cones. So
Yes.
those basically, that's very close to what you say, basically, if not the same. And we know that those fields, they also invoke the axial vertex. So,
Yes.
and that vertex, it comes to with the factor 1/3, which is 1/3, which is applied in this consistent covariant formulation. But in principle, even without going to the field of consistent covariant, one should in principle expect that you may have fields which correspond, you may have phenomena which corresponds to a vertex. So means that in your formula, which is here on the blackboard, one should get 1/3 coefficient. Can you have comment about that?
I know what you're talking about, but we haven't looked at it. It's true. It would be very interesting to explore this synthetic axial
exactly, yes, yeah,
electric fields and see whether you could have some interesting phenomena associated with the corresponding flow of axial current.
Because it should be just 1/3 of the normal current. This 1/3, it's some.
I see exactly what you mean. It's a very good question. So, would be nice first to find some tight binding model in which deformation would induce this synthetic axial electric.
Bonjour, pardon, je suis désolé. Pardon, sorry, just because, yeah.
Because the point is, we found that it's in this particular problem, you really need to have a tight binding model, because things that you think are possible when you look at effective low energy theory, in fact, once you sum over all cones, disappear. So in this case, it's I think it's important to find the corresponding tight binding model, where B5 and E5 could be induced by deformation. But very good point, very interesting question. Thanks.
Thank you.
Okay, we already allowed our time, so let's ask the last question by René, and then we can proceed in Slack.
Okay, yeah, sorry for pushing the time. So I wanted to make a comment on the last comment by Maxime, and also on what Carl said. So and what you were pointing out, Dima. So as far as I remember, these electric times axial magnetic and axial electric times magnetic terms on the anomaly exist in a particular renormalization scheme. This is basically the difference between covariant and consistent anomaly, or something in the middle. And the point is, we have looked at this in a little different context recently, but the point is basically that if you write down some kind of more complete like tight binding model for your condensed matter system that you're looking at, the band structure you get out basically picks its own regularization scheme. Okay, and so it's as you said, it's kind of reasonable to assume that different tight binding models, which correspond to different materials, roughly speaking, will show slightly different effects because they are in a different scheme. Yeah.
Okay, thanks. Thank you for the comment.
Okay, thank you, everyone. Thank you for our speakers. So yes, please continue asking questions in our Slack workspace. I already see there is one question from for Jacopo. So yeah, I mean, hopefully discussion can be continued there, and we will see you all tomorrow for our next day in our workshop. Thank you very much.
Thank you.